Hello guys, welcome to problem 4. In problem 4 we are looking at a radioactivity problem, and it goes this way. A certain radioactive material is known to decay at a rate proportional to the amount present. A block of this material, originally having a mass of Q0 grams, is observed after 24 hours to have experienced a reduction of mass in 10%, okay, of mass of 10%. So find the expression for the mass of the block at any time. Okay, so let's break this problem down one after the other. So solution. So the essence of drawing the bulb all the time is because I believe solution comes when there is light. When you get light to solve a problem, you get inspiration. So that's the essence for me drawing this bulb all the time. Now you want to solve this particular problem, so you're going to break it down one step at a time. So this is a decay problem in terms of radioactivity. There's growth, there's decay problem. Okay, problems like the population problem we saw earlier in problem 2, examples of like growth problems, but radioactivity is basically decay, and you see how this actually affects the nature of these particular problems. Now, a certain radioactive material is known to decay at a rate proportional to what? The amount present. Now take note of the terminologies to decay. So let's assume that M is the amount present at any instant of time. So assume M of T is the amount present at any instant of time T. So assuming that M of T is the amount present at any instant of time T, so what you want to do is you want to now transcribe the meaning of this statement that a certain radioactive material is going to decay at a rate proportional to the amount present. That means the rate of decay, okay, or the rate of change, dm by dt, is actually proportional to what? The amount present. Now, since we are actually dealing with a decay here, it makes sense to introduce a minus sign. Okay, so the rate of decay is proportional to the amount present. So the amount present is m. So the minus sign is because you're dealing with a decay problem here. So don't forget to put the minus sign anytime you're solving radioactivity problem and you saw anything looking like decay. This minus sign is very important. So if you introduce the constant of proportionality, you're not going to have minus km. Is that okay? So this is the model of our system, equation 1. Okay, so they said a block of this material, originally having a mass of Q0 gram, is observed after 24 hours. The mass reduces by 10%. Okay, so find an expression for the mass of the block at any time. Now, from this equation 1, we can separate variables. Okay, separate variables. And when we separate the variables, we're going to get minus 1 over, oh sorry about that, it's usually good to leave the minus sign in the right hand side. So 1 over m dm is equal to minus k dt. So we'll take the antiderivative of both sides. So integral of 1 over m dm is equal to integral of minus k dt. So if you carry out this integration, you're going to get natural logarithm of m on this side is equal to negative kt plus c. And of course, if you take the exponential of both sides, exponential of both sides. You're going to get exponential ln m is equal to minus, exponential negative kt plus c, which we have seen in an earlier video to be exponential kt dot exponential c. So for the sake of this problem, we're going to say let exponential c be m naught. So for instance, exponential ln m becomes m naught, where m naught can serve as original mass, and e to the minus kt, and exponential ln m is m. So in other words, our m of t is actually going to be m naught, original mass, exponential minus kt. So this is like how the graph is going to look like. So you have your m of t, then let's assume we have our m naught starting from somewhere here, m naught. So the graph actually goes like this. It's an exponential graph, it's a decay curve, and the rule governing this curve is m naught exponential minus kt. So we're going to use initial conditions to determine the value of k. Alright, sorry about that. The initial conditions will help us to determine the value of k. So how do we use initial conditions to determine the value of k? Now back to the question. Going back to the question, you can pause the video and go back to the question, but I'm just going to scroll back like this. It said a block of mass originally having a mass of q naught grams. Now I assumed my original mass to be m naught, so I can as well call m naught q naught. It's observed that after 24 hours, it has experienced a reduction of mass by 10%. So the unit of our time is in hours this time around. It's not in seconds, it's not in days, it's actually in hours. And after 24 hours from q naught, there was a 10% decrease. Decrease in 10%. So 10% is actually what 0.1 of q naught. So what will be remaining will be 0.9 of q naught, or 90% of the original amount. So if 10% reduces, then 90% or 0.9 will be present. So let's see how we are going to use this data to obtain our proportionality constant, or our radioactivity constant in this case. So we are given that m of 24 is actually going to be what? 0.9 q naught. So this means that m is equal to 0.9 q naught when c is equal to 24 hours. So this is 0.4 q naught, let me say kilograms or units of mass, or so on and so on and so forth. And take note that our m naught is exactly q naught, according to the initial conditions given to us. Or if you want to solve it the normal way, let me just prove that m naught is q naught. The initial conditions is m of 0 is equal to m naught exponential minus k times 0. So we have m of 0 is equal to m naught. And according to what they gave us in the question, it said that initially we have that the mass is q naught. So m of 0 is actually what? Q naught. So m naught and q naught are the same. So initial is your m of 0. Anytime you say something of 0 is your initial, and we just use an m subscript naught or a q subscript naught to actually represent our initial values. So they now told us that after 24 hours, that quantity that was formerly q naught experienced a reduction of 10%. So they are trying to tell us that what is now remaining is what? 90%. Is that okay? 90% of Q naught, and 90% of Q naught is 0.9 of Q naught. So we want to use this in this our model over here to find the value of K, and what you just need to do is actually to substitute 0.9 Q naught. Anywhere you see M, you put 0.9 Q naught is equal to our M naught is actually Q naught itself, and exponential. Anywhere you see T, you put 24. Is that okay? So Q naught cancels out Q naught. Now 0.9 is equal to exponential minus 24K. Are we together? So when we take the logarithm of both sides, the natural logarithm of both sides, you have ln 0.9 is equal to ln exponential negative 24K. Now follow me carefully and see what I do here. So ln 0.9 now becomes negative 24K. So the reason is that ln exponential f is equal to f. So if you solve it like this, K will now be ln 0.9 over 24. Don't forget your minus sign. Ln 0.9 over 24. So K is negative ln 0.9 over 24. So how do we go about with doing this? How do we go about with doing this? Putting it back into our main equation over here. This is our main model, the one that is asterisk. We're now going to get, let me just write it here, m of t is equal to Q naught exponential minus kt. Okay, so this is the model and this is the value we got for k. So I just want to express k in a more suitable form. Okay, I want to express k in a more suitable form. Now k is actually minus ln 0.9 divided by 24. So this is still the same thing as ln 0.9 raised to the power of minus 1 divided by 24. So I have k to be ln what exactly? So it's still 9 over 10 raised to the power of minus 1 over 24. And if you simplify this, you're going to get ln 10 over 9. When you take it, the reciprocal of 9 over 10 gets 10 over 9. So this is the form that I choose or I prefer to express my k as. So I didn't want to express it this normal way because I don't want this minus sign to cancel out. Is that okay? I want this minus sign to be here. So if I put k like this, the minus sign will cancel out, and I don't want that. You can do it like that for your own, but I feel the minus sign makes it look like a decay equation. So you have q naught and exponential minus, you have ln 10 over 9 divided by 24, and don't forget to put your t. So this is the equation for the amount of substance that actually remains at any time. Okay, the amount of substance that actually remains at any time. Take note, someone else would have solved this particular question using q of t, and the q dt is actually proportional to minus q. Someone else would have taken this approach so that everything would just be uniform in q naught and so on and so forth. Someone else would have solved with m, no problem. So however you express it, just make sure that you have this particular terminologies. So I want you to use Q to do your own, and let's see what you get, if it's going to be the same with my own. So take notes, this is in terms of units of measurement of mass, which for our case is either grams or kilograms, or whatever the unit may be. It wasn't actually specified. So thank you for watching, and see you in the probably the last video for application of differential equations for this series. Don't forget to like and subscribe, and to leave your comments if there's any question or any move I made that you didn't really get, or if there's anything that you feel that I need to be corrected on. You can leave a comment and I'll actually look into it. So thank you so much for watching. Once again, peace.